Okay, so the rest of the information you need on logarithms is called mixed equations. So we're going to learn how to solve some equations using logarithms and also review solving some equations with exponents, since a logarithm and an exponent are just inverses of each other. So if you haven't already tried the top 4 problems, those are review from the previous week with the properties of logarithms. So if you haven't already tried them, if you want to pause the video so that you can try them before I do them, you can do that, or you can just follow along. So remember that if you're expanding uses addition, subtraction, and coefficients. And condensing uses multiplication, division, and exponents, and we should also only have one logarithm. So for number 1, I have the product of x cubed y squared. So that product is going to change to addition, and the exponents are going to change to coefficients. So first thing I would do is write log x cubed plus log y squared, break up the product into separate logs with addition. Remember that if there's no base written, it's understood that it's the common log and has a base of 10. But I'm not finished until I take those exponents and remove those to be coefficients. That would be my answer for the first one. For number 2, I have a quotient. And then recall that we don't have any properties that address what to do with radicals. So before I even get real started, I'm going to rewrite the square root of x as x to the 1/2, because I do have properties that tell me what to do with exponents. I do not have properties of logs that tell me what to do with radicals. So first step is I'm going to break up your quotient into separate logs with subtraction. So the numerator gets its own log and the denominator gets its own log. And then again, I'm not finished until those exponents get written as coefficients. Now that is fully expanded. To go the opposite way, very important to remember there's only one log on your final answer. I want exponents, multiplication, and division. So first thing I see is all the logs have the same base, log base b. So when I'm going the opposite way to condense, first thing I always do is take any coefficients and write them as exponents. Okay, then I have these 2 logs are added. So that's going to change to multiplication, and then the subtraction is going to change to division. So I have one log, log base b, and in the numerator is going to be a times d to the c power, and in the denominator is going to be m. And then number 4 is a little bit of a braid teaser, kind of goes along with one of the examples from last week. Uses one of the properties that says if the base of the exponent matches the base of the log, they cancel each other out. And the natural log has a base of e. So even though it doesn't seem that the obvious base of the log is the same as the base of the exponent, that's what the natural log implies. And so e and natural log will undo each other, and that first term is just going to change to 2. Just like we did last week, we're going to take the exponent rules and work backwards. So exponent rules say if the bases are the same and you're multiplying, you can add exponents. Looks like something's being added in my exponent, so I'm going to take it back in the reverse way, and I'm going to make the base of e squared times the base of e raised to the 2 natural log 3 power. And then I can see that those are equivalent because the rule is if the bases are the same and it says to multiply, I can add my exponents, which is what it says right up here. So remember that e is not a variable. It is a numerical value in a rational number. So e is just going to stay e squared. I don't want the decimal, but it's not something that I'm trying to solve for or anything. And then I have right here, I want to use that property where the base of the exponent matches the base of the log. But first, I need those to be right next to each other. So I have to take the 2 that's a coefficient and rewrite it as an exponent. That allows me to apply the property because now the base of the exponent and the base of the log are right next to each other and they can undo each other. So that'll just be 3 squared, which is 9. And I have 2 plus 9e squared. And that would be my answer. Okay, so here is the new stuff. We're going to break up these equations into 5 types. The first 2 should be reviewed for you. If x is in the exponent, then your strategy should be to get the bases alike and set the exponents equal. This is a review. So 3 is prime, so I'm not going to be able to rewrite that. So it's going to be 3 to the x minus 1. But to make this work, I need 81 to also have a base of 3. So I need to figure out 3 to what power would equal 81. And 3 to the 4th power equals 81. Once the bases are the same, I can make them go away. X minus 1 equals 4. So x is equal to 5 is my solution. The next example is a rational, which is a fractional exponent. So again, we did those actually a couple times this year. So the first step is to isolate the exponent. Then we undo the exponent with reciprocal power and check for plus or minus. Okay, the rule for using plus or minus is if the reciprocal power has an even denominator. Otherwise, you don't need it. Okay, so first step, isolate the exponent. So we need to divide by 2 first. So now y to the negative 2/3 equals 4. Now the exponent's isolated, then I can raise both sides to the reciprocal power, which is negative 3/2. The reason that works is because when you have a power to a power, you multiply, and when you multiply reciprocals, you get 1. So that side just equals y. And I'm going to need plus or minus because the denominator of my reciprocal power is even. So even though it doesn't appear that I'm taking the square root of both sides, that's the meaning of that fractional exponent. It means to take the square root and then cube it. There's also a negative. Remember, negative exponents don't make things negative. They make them move. So this is the same as 1 over 4 to the positive 3/2. And 4 to the 3/2 power is the square root of 4 to the 3rd power, which is 2 to the 3rd power. So my answer is 1 over 8, and again, plus or minus. And now we're going to get into the new stuff. What do you do when you have logs involved in your equation? So there's a couple different ways that your equation that has one log or natural log could look, and different strategies. But if there's only one log, you always want to rewrite into exponential form, which we covered last week. And then if you write it into exponential form, now it has an exponent, so it should fall into one of the first 2 categories because now it'll be exponential and not logarithmic. So you have to choose which exponential strategy you're going to go with that we just reviewed. All right, so for the first example, the logarithmic form would be log base 5 of x equals 2. The exponential form would be 5 squared equals x. And the base of the log is the base of the exponent, and then the other two values just switch sides. And then, so clearly my answer here is just 25. Easy peasy. For the next one, notice my x is in a different place. So my exponential form, the base of the log is understood to be 10. So 10 to the x equals 0.1. So 10 to what power is equal to 0.1? This would fall into the first category where x is in the exponent. So I'd ideally like to get the bases the same. So when you have a decimal, you might want to write it in its fraction form. And that is pronounced 1/10, which is also the fraction form. Then you can kind of see where you're going to get your like bases of 10 to the x on the left, and 1 over 10 would be 10 to the negative 1 power. So x is equal to negative 1. And the last example, again, notice that the unknown is in yet a different place. We still want to write it in exponential form. It would be x squared equals 4. And then this would be, I guess, technically the second strategy, except there's no fractional exponent. You should know what to do here. Take the square root of both sides, which means you're going to need plus or minus. Okay, so you do technically get x equals plus or minus 2. Now, log equations are one type of equation, just like absolute value equations and some other types, radical equations that could have extraneous solutions, because logs have some rules, mainly that the base of the log and the number next to the log can't be negative, can't be 0, and also the base of the log can't be 1. So the base of the log and the number next to it have to be positive, and also the base can't be 1. So that means that I'm going to have to discard x equals negative 2 and just settle with x equals 2, because of the base of the log cannot be negative 2. The next type of log equation is if we have more than one log. So here's where those log properties from last week are really going to come in handy. We're going to use our log properties to condense. You're only allowed one log per side. So for the first example, I've got 2 logs on the left and a single log on the right. Well, I've got too many logs on the left. So I'm going to use my properties to condense that to a single logarithm. So the 2 logs subtracted will condense to 1 log using division. And then similar to when it's exponential and the bases match on both sides, you can just cross that out. If you have a single logarithm on both sides and they have the same base, I can cross those out. So my answer is x equals 7. Again, you do want to check for extraneous solutions. There's no problem with any value of 7 if you were to substitute back in, because the number next to a log just has to be positive. So the next example, this would be probably the easiest scenario. You have 1 log per side. They both have the same base. And so I can cross out the log base 7 and make an equation out of what's left. And you get x equals 6. Again, you do want to check for extraneous solutions. If I plug 6 back in, it does not create a situation where these values are negative. So fine with that. Got a couple more examples here. So the next example, it does look like, well, I just have 1 log per side, so that's good. But you need each of those logs to be in their condensed version so that it literally is log equals log. And right now that 3 is sort of in the way. So if we condense, we take that coefficient and we move it to be an exponent. And now I have log base 10 equals log base 10, so I can get rid of it and solve x cubed equals 27, would take the cube root of both sides, and x needs to be 3, and again, not extraneous. Last example in this section, I have 2 logs on the left and 2 logs on the right. So I need each side to only be a single logarithm, and I do that by condensing. So I'm going to move this coefficient up to an exponent, and I'm going to rewrite this as 1 log, because the 2 logs added, I can change to multiplication. So over on this side, it would be 0.1 x squared. And over here, I would condense these 2 logs to 1 log by taking the 5 and the 2 and changing it to a product. So that'd be 5 times 2, and I would get 10. Then I can cross out the log on each side. So I have 0.1 x squared equals 10. Can divide both sides by 1/10. That equals 1/10. So I can either divide by 1/10 or I can multiply by the reciprocal, which would be 10. And then if you take the square root of both sides, you do get plus or minus 10. But remember, the base of the log can't be negative, and the number next to a log can't be negative, and so negative 10 would be extraneous. I want to emphasize that the solution to a log equation can, in fact, be negative. It just can't be used if when you substitute it back in. It makes the base be non-positive, or the number next to the log be non-positive. So you do want to check that. Don't assume because you get a negative answer, you automatically throw it out. All right, the last type of log equation starts out as exponential, but it's sort of the reason that we need logs to solve some types of equations. So this kind of goes back to the first type, except in the first type, we could rewrite one or both sides to make bases match. And here, that's impossible. There's no way to rewrite a 7 or a 20 to make them have the same base. 7's prime, and I certainly can't write 20 in terms of 7 to some power. So if it's exponential, where x is in the exponent, but it's impossible to make the bases match, we're going to use logarithms to help us solve these. Our strategy is going to be put either common log or natural log on both sides. Completely your choice. And then we are going to expand exponents. So in the last set of examples, we wanted to condense. Now we're going to do the opposite. We're going to expand. Okay, so it's, again, your choice, log or natural log. Students tend to just like writing log. They're not real comfortable with whole natural log. In pre-calculus, there will be some types of equations where you have no choice. But I'm going to use log because I know that's what students usually feel better about. So never going to make these bases match. So I'm going to write log on both sides of the equation. Remember, you can do anything to an equation as long as you do it to both sides. Then I only have the one exponent, but I want to expand that exponent to be a coefficient. And now I can isolate x by dividing both sides by log 7. So x is equal to log 20 divided by log 7. There is no way, like you can't do anything with that. It's just the answer. That's called calculator ready form. And it actually goes back to the change of base formula that I showed you last week. So that could have also been natural log 20 divided by natural log 7. So this is the exact answer. And then if I wanted the approximate answer, I could put that in a calculator. So your second example is going to be a little bit more involved. Again, there's no way to rewrite this to make a base of 2 and a base of 5 ever match. They're both primes. It's just not going to happen. So I'm going to put common log on both sides. Then I'm going to expand those exponents to coefficients. Since this exponent's a binomial, I want to put it in parentheses. Any exponents that are binomials, you're going to need to distribute. Okay, non-negotiable. So over there on the right, I'm going to distribute and write that as x times log 5 plus 2 times log 5. So here's the thing. I'm trying to solve for x, but I have an x on the left and I have an x on the right. That's an issue. So in order to solve for a variable, I need that variable to at least be on the same side of the equation. Doesn't matter if it's left or right, but those two x terms need to be on the same side. So I'm just going to subtract x log 5 to get it moved to the left. And now when I do that, it creates a situation where these two terms both have x. That makes x a common factor, which means I can factor it. And once I do that, to isolate x, I can just divide both sides by what's in that parentheses. And my calculator ready form is 2 common log 5 divided by common log 2 minus common log 5. There are some other ways that you could write that, but that's considered calculator ready form, so that if I wanted an approximate answer instead of the exact answer, that's what I would type in the calculator. And there will be times when you won't have a calculator, so you need to know how to get it into calculator ready form. And also sometimes it's important to have an exact answer and not have a rounded answer.